Hello, this is IT Taro. This time, I would like to investigate the temperature sensor. I would like to use a temperature sensor, such as attaching a temperature sensor to the smart remote control I made before and controlling it by temperature, but there are so many that I don't really understand. Therefore, when actually using it with ESP32 this time, I would like to purchase candidate products and investigate. We will investigate 11 temperature sensors with prices ranging from 40 yen to 480 yen. The performance of the sensor itself is disclosed in detail in the datasheet from each manufacturer, so that is the correct information. This time, it is based on research by IT Taro, so please check it as one piece of data using ESP32, which is a microcomputer with Wi-Fi. Let's start with the table of contents. Here is the table of contents. First, I will introduce the list of sensors to be investigated. We will also understand the differences in specifications. In the second item, confirm the ESP32 port. Accuracy also affects the performance of this port, so understand what the specifications are. In the third item, we will understand the specifications of each sensor, and check the circuit configuration, temperature calculation method, etc. Next, I will check the circuit I measured this time and introduce the measuring equipment. Finally, we will proceed with the announcement of the survey results. Move on. Here is a list of temperature sensors that we will investigate this time. The selected standard is a sensor compatible with 3.3 volts or 5 volts, and the measurement range is from 0 degrees to 40 degrees, which is normal room temperature. In addition, 11 pieces were selected in order from the lowest price. I thought I would limit it to 10, but the last DHT11 had a separate function for serial communication, so I chose these 11. The scope of the survey is the result of surveying stores in nearby electric towns and reliable mail-order shops. There were some products that could be procured at about 1/10 of the price in overseas mail order, but I doubted that they were legitimate model numbers, so I didn't use them. To the end, according to IT Taro's research, there are 11 of them. We will check the specifications of each sensor individually. Move on. This time, the specifications of the temperature sensor to be investigated are summarized as follows. First of all, I think that it can be roughly divided into two. One is a sensor that displays temperature by voltage output, and the other is a sensor that holds temperature data inside the sensor and outputs data via I2C or serial communication. In the case of voltage output, for example, 1 volt represents 0 degrees, and the output is 0.1 volts every time it rises by 1 degree. All of the sensors used this time have a linear relationship between voltage and temperature that can be represented by a linear function. In the case of voltage output, the measurement accuracy of the voltage value is related to the temperature accuracy, so it must be accurate. We will use the ADC port that can measure voltage with ESP32, but this measurement accuracy will be affected. In the case of data output, there is no measurement with the ESP32, so it is possible to obtain the sensor accuracy as it is with the ESP32. In that sense, when used in a microcomputer, data output tends to be more accurate than voltage output. This table was evaluated based on IT Taro's own criteria. Judgment may change depending on what to focus on, but it will be used as a reference in advance. It seems that it is a voltage output type in terms of price and a data output type in terms of accuracy. Think. Move on. We will also measure after understanding the terminals used by ESP32. This time, instead of using a genuine espressif development board, we will use a 15-pin double-row development board made by another company because it is inexpensive. Of course, it is a product that corresponds to technical standards. Regarding the ADC terminal, ESP32 has two ADC circuits. The ADC circuit is an abbreviation for analog to digital converter, and it is a circuit that can acquire analog voltage values. Since the obtained value and voltage have a linear relationship, for example, if a value of 1000 can be obtained, it can be converted to about 0.8 volts. Also, since the ADC circuit has an 11 decibels attenuator inserted as standard, it is possible to measure from 0 to 3.3 volts. If the attenuator is not inserted, it is possible to measure from 0 to 1 volt. Just to be sure, I set the attenuator to 0 decibel in the program, and it certainly measured 0 to 1 volt. Since the resolution is 12 bits by default, it is possible to acquire values from 0 to 4095. If this value is set to 10-bit, it will be possible to obtain values from 0 to 1023. This time, we will use the standard values for the attenuator and resolution due to the measurement range. As a point of caution, I think that the limitation that the second ADC circuit cannot be used with Wi-Fi has not been improved yet. Since two ADC circuits are used this time, the network cannot be used, and the data is acquired by displaying the data on the serial monitor. Next, I2C is a method advocated by Philips, and is one of the synchronous serial communication methods. Along with SPI, it is often used for data communication between microcomputers and sensors. In ESP32, I/O21 and 22 are assigned, so use those ports fixedly. Since the device to be connected has a fixed address, it is possible to connect multiple sensors at the same time and communicate if the addresses are different. Move on. Understand temperature sensor ICs. The appearance of the 6 temperature sensor ICs that output voltage is almost the same. If you don't check the model number with the printing on the surface, you can't identify it by appearance. The method of using the terminals will be the same. A typical circuit is shown in this figure, so connect a 0.1F capacitor between the ground and VDD. Also, the relationship between the output voltage and temperature is 500 mV at 0 degrees Celsius and increases by 10 mV for each 1 degree Celsius rise, so the formula for calculating the temperature from the voltage is as follows. We will program this formula. Move on. Programming the temperature sensor IC goes like this. Define an ADC port and set it to be used as an ADC circuit in the setup function. Get the voltage in MV units in the loop function and convert it to temperature using the formula. Finally, output to the serial monitor. Although the calculation formula is different, programming is similar for other voltage output type sensors. Therefore, I will omit the confirmation of programming from now on. Move on. This sensor has almost the same specifications as the MCP9700 mentioned earlier. The circuit configuration and calculation formula are also the same. Move on. This sensor is a type that acquires information in the sensor with I2C. Therefore, there is no need to measure the voltage with the ESP32, so you can use the temperature purely measured by the sensor. Therefore, it is estimated that the error tends to become smaller. I2C is assigned an address to the device. This sensor can change the address by connecting the terminals. This time, all of them are connected to the ground and used, so 48 addresses in hexadecimal are used. Also, since the data to be acquired is shifted 4 bits to the left, the temperature is calculated with a 4-bit shift in the program. The program was created with reference to the reference URL shown in the upper right. All the programs used for the measurement are published on the Hobby IT site. Move on. This sensor is compatible from 5 volts, but it is a sensor that is used at a relatively high voltage. Output is 10 mV per degree from absolute zero. Therefore, when converting to Celsius, subtract at 273 degrees. Move on. This sensor has a 0 degree of 600 mV, and the voltage increases by 10 mV per degree. Therefore, the calculation formula is as follows. The circuit is ready to measure the voltage output by connecting the positive power supply and ground. Move on. This sensor has 424 mV as 0 degrees. Since the voltage increases by 6.25 mV per degree, the temperature can be obtained with this formula. The circuit can be measured with the same circuit as before. Move on. This AHT25 is a type that acquires data by I2C. Since there is temperature information inside the sensor, it means to acquire that value. The I2C address here is fixed at 38, so we will use this address for programming. Also, since the data has a CRC code attached, please understand this. CRC is data added to check whether the data is correct due to noise in data communication. It has nothing to do with the data itself even if it is not checked. However, if it is not checked, it will not be possible to detect any errors in the data. There is little noise like this time, and I don't think there is any tampering from the outside, so the check may not be necessary, but I will refer to the reference URL and create a program to perform the CRC check and measure it. Again, the program used for the measurement is published on the Hobby IT site. Move on. This OT21B is also a sensor that acquires data by I2C. A library is provided for programming, so you can use it without being conscious of I2C. Using a library makes it easy to program, but it also has the disadvantage of making it difficult to understand the detailed operation of I2C, etc., making it difficult to improve and improve. This time, I2C is programmed with another sensor, so this sensor is used as a library. Move on. This DHT20 is also a sensor that acquires data by I2C. A CRC is attached to the data, but this time I omitted the check in the programming. This is omitted because the possibility of errors in data is low and the program for checking CRC with AHT25 is created. The program itself was created by referring to the reference URL. Move on. This DHT11 is a type of sensor that acquires data through serial communication. Communication is handled by the library, so it can be used easily. For I2C, the ESP32 terminal is fixed, but this serial communication can use the normal I/O terminal. The circuit that uses this sensor uses only 3 of the 4 terminals. One pin is not connected to anything. Follow this circuit diagram to wire and use. This concludes the description of the sensors to be used. Next, I will check the circuit diagram used in the measurement. Here is the circuit diagram. I made wiring for one sensor for each ADC circuit so that there is no influence between sensors. The left side is the wiring for the ADC circuit. On the right side is the circuit that acquires data via I2C. 2 devices with different addresses are connected to the I2C terminal. Since the I2C signal voltage must be 3.9 volts or less, 5 volts is not used, and the sensor is driven at 3.3 volts. That's it for the circuit. Here we measure the temperature data of the 4 sensors. Move on. This circuit is basically the same as the previous circuit. I am creating a circuit based on a data sheet. This circuit acquires data from 3 sensors. Move on. This circuit is basically the same as the previous one. However, DHT11 acquires data by serial communication. It uses IO32, which is a normal terminal. This circuit acquires data from 4 sensors. 11 sensors are investigated with the above 3 circuits. Move on. In order to measure the temperature as accurately as possible, I prepared 4 commercially available thermometers. However, this is also not high performance, so I do not know how accurate it is. Therefore, we excluded the values that clearly deviated from the measured values, and used the remaining average value as the temperature of the measuring instrument. We will measure how much error there is from this temperature. Since the room temperature is raised, there is also a follow-up speed to the temperature change. Considering these factors, measurement error will occur to some extent. Move on. First, check if the measured value of the ADC circuit is correct. I have verified that they are equivalent in the tester. In general, it was good, so I confirmed that there was no problem. Move on. For the measurement environment, 4 thermometers were placed in a surrounding shape and measured. Also, some sensors have noise in the voltage output of temperature sensor ICs, and there are variations, so we averaged 2 times by excluding specific values that deviate greatly. Move on. Here are the measurement results. Please exclude LM335Z and LM60 because we were unable to obtain normal values. I don't think the sensor itself is the problem. There was a problem with the circuit or calculation formula, or there was some other problem that prevented normal values from being obtained. Even if I prepared another new ESP32, it could not be used, so I think that it is not a problem on the ESP32 side. I think there was something wrong with the usage of the sensor. I feel that a little skill is required, so I will exclude it this time because it is not for beginners. As shown in the graph on the left here, it can be said that all the sensors are able to measure the temperature as per the specification and there is no problem in general. The graph on the right shows the cumulative total of errors. As expected, the data output sensor tends to have a smaller error than the voltage output sensor. According to this result, OT21B had the smallest error, followed by AHT25 and then DHT11. However, none of them can be said to be a large error, and when various measurement errors are included, my impression is that there is not a large difference in practical use. This is the result of the temperature sensor measurement. Next time, I will present the results of the humidity sensor. I would like to deepen my understanding of I2C programming at the next humidity sensor. Also, when using both temperature and humidity sensors, I would like to consider which one is better overall, such as price and ease of use. This is the end of the temperature sensor results for this time. We will continue to take on the challenge of making things using IT like this, so please give us a high rating and subscribe to the channel. See you next time.